Yeah, okay, so I'm actually here at CU Boulder, like 2 buildings over. And my name's Katie Primm, and the title of my talk is really large. Supercooling and ice formation of perchlorate and chloride brines under Mars-relevant conditions. So the images you see here are from The Martian, the movie. So if you haven't seen it, I would like close your ears and eyes and stuff because it's a really good movie and book, so I would watch it. But if you have seen it, you remember Mark Watney. He's trying to make potatoes for himself because he's alone on Mars and he needs to live. But in order to make the potatoes grow, he needs water. And so he ends up combusting H2 and O2 to make water. But he ends up getting a buildup of O2 and then blowing up right here. So the theme of my talk is water on Mars. So as you might know, since we've been talking about Mars for a while, there's quite a few differences. So the pressure on Mars is about 100 times less. It's 830 millibar here in Boulder. So normal sea level is 1,000 millibar. Average temperature is 70 Kelvin less or so, and the water vapor is about 10 times less. So considering these conditions, what water phases do we know exist on Earth today, or Mars on today? So we know from the Viking Lander, it took an image, saw all these rocks and iron-rich minerals, and then it woke up again and saw that frost had deposited on the surface. And so we know there had been water in the atmosphere and then it deposited onto the surface. So this is like the northern plains or so of Mars. And then the Hubble actually took images of the North Polar Cap and saw this white stuff, and it actually almost disappeared. And what's left is actually due to water ice. So we know we have frost. And then, of course, our cells, you might know, recurring slope lineae, if you don't know what that is. It's just these dark streaks that look like flowing water on Mars. So this is higher elevation, lower elevation. See these dark streaks going in? So this is evidence we have of liquid water on Mars. As you might be thinking, in September, if you watch NASA TV, they had this big announcement saying, oh my gosh, there's water on Mars and stuff, and this paper was published. And if you actually read the paper, they say that they're hydrated salts, and they don't actually say they found water. They just say in order for hydrated salts to be on Mars, you have to have a liquid phase. But hydrated salts alone might not be indicative of liquid water, because if you have a hydrated salts, you can have an anhydrous salt, increase the relative humidity, and then get a hydrated salt. Or, which this doesn't have a liquid phase, or you can have an aqueous salt solution, lower the relative humidity, and get a hydrated salt. So there's a couple different ways to have a hydrated salt, and you don't always need liquid water. But I'm going to be focusing on this aqueous salt solution and hydrated salts. So in order to understand everything I'm going to be talking about, you need to know the pathways of liquid water that could be possible on Mars. So if you're starting with a salt crystal and you have water vapor, in this case sodium chloride, you increase the relative humidity, you get a liquid. And this is actually called deliquescent, so I might be throwing that word around. So if you think about temperature and relative humidity space, lower relative humidity here and higher relative humidity over here, you have some solid crystalline salt. You pass some threshold of relative humidity and temperature, and you can get a liquid. So I'm going to be showing a video that starts with this crystal, and then it turns into a liquid droplet. So you see here, it starts to darken, and now it's a liquid. So this is actually what I do. I actually study how this phase transition happens, this deliquescence. But if you're lower than freezing point, or higher than that, you can get ice. So if you're starting with this liquid region, past some other relative humidity temperature threshold, you can get ice form. So again, I'm going to show another video starting with the liquid phase of this turning into an ice particle. So it's liquid, it grows, and it starts forming ice here. So this is ice. So these are all the phase transitions that you can think about for what could be possible on Mars, because we know there's not just liquid water because of the pressure and the temperature. So I actually study at what points these things happen. So where's the liquid region, where's the ice region, where's just the solid salt? So you also might be thinking, well, we're just going this way, increasing relative humidity. Is there any difference from decreasing relative humidity? So if you decrease relative humidity from a liquid, you get a salt crystal back. Uh-oh, what do I mean? You actually get efflorescence. And it's interesting because efflorescence doesn't happen at the exact point of deliquescence. It actually has hysteresis. So hysteresis is if you have a crystalline salt, you increase the relative humidity at some DRH, or deliquescence relative humidity, you get a liquid droplet. But if you're over here past the deliquescence relative humidity, you decrease the relative humidity, you won't get a crystal back here. You actually have to decrease the relative humidity even more until this efflorescence relative humidity, which is more commonly below the deliquescence relative humidity. So the history of the salt particle is important because if you're in this region of relative humidity, depending on if you started with the crystal or started with the liquid, you don't actually know what phase transition or phase you have. So which salts do I want to study and why? Because we have all these salts on Mars and what's interesting for water. So this is Marvin the Martian, if you don't know. So I'm studying perchlorate and chlorides because the Viking Lander found both of these, and more specifically perchlorate in 0.5% by mass. And I want to study these because they're globally distributed, and both of these are highly deliquescent. So they take up water vapor at a low relative humidity. Oh, oops, sorry. Okay, so how I actually do this, I make solutions of magnesium perchlorate and chloride in water. I nebulize them onto this quartz disc shown here, and then I stick them into my Raman microscope. So our Raman microscope is kind of special because, well, it's a Raman microscope, so it's kind of cool. It has a Raman spectrometer, has a CCD camera, so you can actually look at what you're seeing. And we have it outfitted with a sample cell. So in the sample cell, we have a liquid nitrogen temperature controller and a humidity controller. So we can actually make the conditions like Mars. And in addition, since we have our particles on this disk, we can see what the particles look like on a micron size basis. So let's get into this. Magnesium perchlorate. So this is actually magnesium perchlorate, not something else. So what we know now, magnesium perchlorate, some studies by Goff et al. Found the deliquescence relative humidity around 40 to 50% RH at this, along this model line. And then they found the efflorescence, efflorescence relative humidity, again, has hysteresis, so it's lower than the deliquescence relative humidity, around 20% RH. So I wanted to study exactly, since we know the deliquescence and we know the efflorescence. We have this model here saying that ice should form here, but does it actually form here? So I do a trajectory. So I start with the solid, I go through the liquid phase, and I see exactly what point water ice forms on this salt. In order to do that, I have to know how this Raman microscope technique works. So over here is an image of magnesium perchlorate crystal. So this is an individual particle, and this is a size bar. And this is the Raman spectrum that I see. So this is the OH region, and this is the perchlorate region. So here at 0% RH, you have the hexahydrate, you have a little peak hydrate, sharp peak from the hydrate, and then the perchlorate just over here. So you increase the relative humidity to around 50% RH, and you get deliquescence like we've seen before. So you see this particle is now homogeneous and looks liquid. And this hydrate peak actually is broadened because of unbound water. And you might see as we keep going, the perchlorate peak doesn't change. Increase the relative humidity even more to 95%, and you get ice form. So you see it especially in the OH region, and you see it optically. So then now we decrease it, and at 59% RH, we get the liquid again. And then farther, 25% RH, we get still a liquid, and it's below the deliquescence relative humidity. And finally, at 0% RH, we get the hexahydrate back again, so a crystal. So I repeat these studies over and over again and see at different temperatures where does this ice actually form. And I actually get this. So you can see deliquescence here, efflorescence here. And ice actually doesn't form on this theoretical model line. It actually forms a little bit past here. So supersaturation actually occurs. And so if you think about the different regions of liquid phase that could be present for magnesium perchlorate, with using just models, you have this part of the liquid phase here. But if you think about my studies, you actually have an extension of this liquid phase over here. So we can have liquid for even longer. And if you decrease the relative humidity from the ice, you can have even more metastable liquid because of efflorescence. So to relate this to Mars, because this is all temperature, or not all temperatures, a wide range of temperatures and relative humidities, we can plot a diurnal cycle on this and then see exactly how long liquid water could be present due to the deliquescence and ice formation of magnesium perchlorate. So if I plot this same profile on a time versus relative humidity scale. So this is noon to noon. We can see exactly how long liquid is present. So noon to around midnight or so, we have a crystal, and then deliquescence starts to happen here. And then this red line is that theoretical ice line where ice, they say, should form. But with my studies, the liquid region is actually extended for almost 2 hours longer than previously thought. So we can have liquid for longer. And then finally, you have ice again, and then due to melting and efflorescence, we have more metastable liquid. So for this particular Mars diurnal cycle, liquid water is present for almost 2 hours longer. So again, this is magnesium perchlorate. There are other salts on Mars. So what about magnesium chloride? Because this is also found on Mars. So I did the same types of studies for magnesium chloride, and I see that for this particular diurnal cycle again, liquid water is present for over half the day. So again, noon to noon, and it's present for a really long time. And this is again in the theoretical ice line, and then I've extended it for almost an hour through my studies. So to relate this back to astrobiology and other things like analogs on Earth, so we have Don Juan Pond in Antarctica. Oh, can you see this? Maybe not. Yeah. Okay. So this actually is looks like a river type channel, and this is the relative humidity profile. So at point A, it's around 15–18% RH here, and you can kind of see this little streak. And then it shoots up to around 100% RH at B, which is this image. So you can see it has darkened, just like an RSL on Mars. So this is also some other proof of liquid water present on Mars. And about life on different planets, you can have, so this deliquescence that can happen on different salts can actually help cyanobacteria or other organisms obtain water and actually live. So this is a vaporite rock, and this like gray line that you see here is cyanobacteria, and it's covered. It has a layer of NaCl, and so the NaCl is actually deliquesced, takes in water, and then the cyanobacteria uses that water to actually grow and live. So just some conclusions. So deliquescence of these salts on Mars could be an explanation of how water is present on Mars today. And evidence of organisms living in salty brine conditions on Earth could be an analog of life on Mars. Just thank my group and NASA and NSF for funding, and you guys have questions? This is Britney Spears. Do you remember this thing?
Really interesting study. I'm curious, did you take into account pressure?
Yes. So the studies for our Raman microscope before I started doing this, and a couple other people, they did it on Earth, and so they did it at ambient pressure, and they're like, whatever. And so we were like, oh, we can actually do Mars stuff. So we just kept it at ambient pressure. So all this is at ambient pressure. But we actually, in like the next couple of weeks, we're gonna lower the pressure and we do nitrogen, so we're gonna add CO2 and see how that affects it, yeah.
Other questions? All right, if there are no further questions, we'll move on. Thanks.